Let us see a brief introduction to irrational numbers. In 5th century BC, famous mathematician and philosopher Pythagoras and the Pythagorean in Greece were the first persons to introduce the numbers which are not rationals, that is, irrational numbers. Initially, Pythagoreans proved that root 2 as a rational number. Then after, Theodorus of Cyrene proved that root 3, root 5, root 7, root 9 and so on are also irrational numbers. About pi. Pi is defined as the ratio of the circumference c of a circle to its diameter d, that is pi equal to c by d. As pi is in the form of ratio, there is no common unit to measure the circumference c and diameter d of the circle. Either c or d should be irrational if we want to measure accurately. So pi is regarded as irrational. The Greek genius Archimedes first computed the value of pi, and he showed the value of pi lies between 3.140845 and 3.142857. The great Indian mathematician and astronomer Aryabhatta, 476 to 550 AD, found the value of pi correctly to 4 decimal places, that is 3.1416. Pi equal to. The decimal expansion of pi is non-terminating and non-recurring. So pi is an irrational number. An approximate value of pi is 22/7. Albert Einstein was born on March 14, 1879, and the same day it is celebrated as Pi Day. Now, let us learn how to represent irrational numbers on a number line. Before going to learn the representation of irrational numbers on a number line, we need to know about Pythagoras' theorem. The Pythagoras theorem states that in a right-angle triangle ABC, the line opposite to the right angle is hypotenuse, and it says that hypotenuse square is equal to the sum of the squares of other two sides, that is, as shown on screen. Now, let us go back how to represent the numbers with roots on a number line. Here, let us represent root 3 on a number line. Initially, draw a number line, mark point 0 on it. Either sides of 0, mark the points -2, -1, 1, 2 with equal set of distances as shown. Now, with the same distance from 0 to 1, draw another line with right angle at 1 and then join these points as shown. Let us mark the points of right angle triangle as OAB. Now, to find the distance between OA, we use Pythagoras theorem. From Pythagoras theorem, OA is equal to square root of OB square plus BA square, which is equal to square root of 1 square plus 1 square, that is root 2. So, the distance between OA is root 2. Now, draw the perpendicular line to OA of unit length and mark it as D. Now, join OD. Then take OD as radius, that is length of root 3, and construct a circle such that it meets the number line and mark the intersecting point C. So, the OC is also radius of the circle, which is the representation of root 3. Now, let us discuss about real numbers, rational numbers. The numbers which can be written in the form of p by q, where p and q are integers and q not equal to 0, are known as rational numbers. Irrational numbers. The numbers which cannot be written in the form of p by q, where p and q are integers are known as irrational numbers. The combination of rational and irrational numbers is known as real numbers. Now, let us observe the conversation on real numbers. Hi Raju. Hi Venkat. I have one doubt in real numbers chapter. Can you clear it? Yeah, for sure. On a number, if we represent all rational and irrational numbers, will there be any numbers which are not covered in the number line? No, Venkat. As we know that the combination of all rational and irrational numbers are called real numbers. So these real numbers cover all the points on a number line. And there will be unique representation of real numbers on a number line. Hence it is also known as real number line. Can you give some examples? Yeah, some of the examples of real numbers are -4, 0, 1, pi, √9 and so on. Now, let us solve some example problems on irrational numbers. Find two irrational numbers between 0.12 and 0.13. Solution. Let the given numbers be a equal to 0.12 and b equal to 0.13. We observe that the given two numbers are irrational numbers and a less than b. Since by comparing both the numbers after the decimal point, the first digit is same in both the cases and the second digit of 2 is lesser than 3. Now, let us write some numbers such that greater than a and lesser than b. They are 0.121, 0.122, 0.123. Now, add some non-terminating recurring decimal to these numbers as shown on screen. Let us assume these numbers as C, D, E. Thus, we conclude that the numbers C, D, E are irrational. Therefore, A less than C, less than D, less than E, less than B. Find two irrational numbers between 3/2 and 7/2. Solution. Let the given numbers be A equal to 3/2 and B equal to 7/2. We observe that both the numbers are rational since they are in the form of P by Q, where Q not equal to 0. Initially here, we need to find the decimal expansions of the given two numbers. The decimal expansion of 3/2 is 1.5. And similarly, the decimal expansion of 7/2 is 3.5. Now, represent the two decimal numbers on a number line. The irrational numbers between these two numbers should lie in between 1.5 and 3.5. So, let us consider some numbers like 2, 3. By adding some non-terminating, non-recurring decimal to these numbers, we get two irrational numbers. Find an irrational number between 4 and 6. Solution. If a and b are two positive rational numbers such that ab is not a perfect square of a rational number, then root ab is an irrational number lying between a and b. Therefore, an irrational number between 4 and 6 is root of 4 into 6. By solving further, we obtain it as 2√6. Let us do an activity on constructing the square root spiral. Take a large sheet of paper, pencil and scale. Mark point O on it and draw a line segment OA of 1 unit length. Now draw a line segment AB perpendicular to OA of same 1 unit length. Joining OB using Pythagoras theorem, we know the distance between OB is equal to root 2. Again, draw a line segment BC of unit length perpendicular to OB. Join OC where OC equal to root 3. Draw a line segment CD of unit length perpendicular to OC. By continuing the same process, finally we obtain the spiral made of line segments as shown on screen. Note that the line segment OA, OB, OC, OD and so on represents the lengths root 2, root 3, root 4 and so on respectively. Representation of real numbers on the number line through successive magnification. Visualize 3.765 on a number line using successive magnification. We know that 3.765 lies between the interval 3 and 4. To have a rough idea for locating it on a number line, make 10 equal parts and mark them as 3, 3.1, 3.2 and so on up to 4 as shown. Now look the portion in between 3.7 and 3.8 using magnifying glass and realize that 3.765 lies between 3.7 and 3.8 as shown in figure 1. So, let us now divide this portion into 10 equal parts and represent them as 3.71, 3.72, so on 3.8 as shown in figure 2. As before, now we can visualize through the magnifying glass that 3.765 lies in between 3.76 and 3.77. So, let us focus on this portion of number line as shown in figure 3 and imagine to divide it again into 10 equal parts. Thus magnify it to see it better as in figure 3. This is how the terminating decimal expansion on a number line is represented. Now, let us represent non-terminating recurring decimal on a number line. Visualize 4.26 bar on a number line using successive magnification. Here, the repeating decimal 4.26 lies between the interval 4 and 5. To have a rough idea for locating it on a number line, make 10 equal parts and mark them as 4.1, 4.2, so on up to 5 as shown in figure 1. Now, look the portion in between 4.2 and 4.3 using magnifying glass and realize that 4.26 lies between them as shown in figure 2. So, let us now divide this portion into 10 equal parts and represent them as 4.26, 4.261, so on up to 4.27 as shown in figure 3. As before, now we can visualize through the magnifying glass that 4.2626 lies in between 4.262 and 4.263. We can proceed endlessly in this manner and simultaneously imagine the decrease in the length of the interval in which 4.26 bar is located.